Hi everyone, in today's video we're going to work through our discussion on transition metal catalyzed reactions, and we're going to start with the reaction known as the Stille coupling. It is my hope that by the end of this video you'd be able to identify the transition metal and ligands that are found in organometallic complexes. You would be able to differentiate between L-type and X-type ligands on organometallic complexes. Within the organometallic complex, you'd be able to determine the oxidation state of the transition metal. You'd also begin to determine the electron count around the transition metal center, and then use that to determine how stable the organometallic complex is. And then you also start identifying the major product, proposing appropriate reagents, and identifying the catalyst that is required to undergo a Stille coupling, as well as identify the stages in the catalytic cycle for your Stille coupling. You're able to understand what the likely rate determinant step is and the factors that affect the rate of a Stille coupling reaction. So we're going to begin with an overview of the components of an organometallic complex. And we're going to use a molecule called Cisplatin, which is an anti-tumor drug, to go over the components of an organometallic complex. And here's what Cisplatin looks like. There's a platinum transition metal at the center of this complex. There are two chlorines that are attached to that platinum. We are going to call these two chlorine species X-type ligands, and we will explain what that means. There are also two NH3s attached to that platinum, which we're going to call L-type ligands. And so for the next few slides, we're going to go over what that transition metal is, how do we characterize it. We're going to go over the X and the L-type ligands as well. So at this point, it might be helpful to pull up a periodic table. Transition metals can be found from groups 3 to groups 12 on the periodic table. They're also called the D block because at the valence shell, the last orbitals to be filled are D orbitals. It is important to note that when you're looking at the rows of a periodic table, so let's just pick any row, let's pick row 4 of the periodic table. At that row or that period, while the S block, which is on groups 1 and 2, would take on the same row number as the period. So let's say you're on row 4, the quantum level for the S block will be n equals to 4. When you get to the D block, however, that quantum level goes down 1. So at row 4, the transition metals from groups 3 to 12 would have an energy level of n-1, which would be 3. However, the actual energy levels for a 4s versus a 3d is actually very similar. And so we typically count all the orbitals across the 4s and the 3d as valence orbitals, and the electrons within the 4s and the 3d, they are all counted as valence electrons. So let's use an example. So find nickel on the periodic table. Nickel is on row 4 or period 4 and group 10. The electronic configuration of nickel can be written as all the electrons and electronic configuration from argon, which was the noble gas 1 row above on period 3, including 2 electrons in the 4s orbital and 8 electrons in the 3d orbital. The 4 and 3 represent the quantum levels that your s and d orbitals respectively are existing in. So once again, the 4 matches the period 4 for the s orbitals. The 3 is 4 minus 1 for the d orbitals. However, we count all the electrons in the 4s and the 3d as all valence electrons. So in this case, there are 10 valence electrons in a neutral nickel atom. Okay, so now let's move over to our ligands. We treat all ligands in organometallic complexes as Lewis bases, meaning these Lewis bases or ligands serve to donate electron pairs into the transition metal complex. There are two types of ligands. The first of which is called an L-type ligand. An L-type ligand is a ligand that if you hypothetically dissociate that ligand with the bonding electron, so those two electrons that are used to form the bond to the metal, if you dissociate that ligand from the metal center, that ligand will be a neutral molecule. As such, when it comes to electron counting, we think about those bonding electrons as belonging entirely to the L-type ligand. As a result, from an electron counting perspective, the removal of this ligand does not change the charge of the metal in the organometallic complex. Okay, so let's see this in action with our cisplatin example. Okay, so once again, here is cisplatin. And note that our NH3s are the L-type ligands in the cisplatin complex. If we hypothetically remove one of the NH3 ligands in addition to the two electrons used to bond to the platinum, the resulting complex, so your platinum complex, does not change its charge. So platinum stays the same charge as it was when it was bound to that NH3. And the NH3 that has been removed is a neutral molecule. That is ammonia. And that is why we called NH3 an L-type ligand. And we will see how L-type ligands affect counting how many electrons are around a metal, the oxidation state, and what have you. On the other hand, X-type ligands are anionic in the hypothetical reaction where you dissociate that ligand from the metal center. And you take with you the bonding electrons used to form a bond between that ligand and that metal. When we think about the bonding of this particular X-type ligand, we consider it as a typical covalent bond where we assign one of the two electrons to the metal and one of the electrons to the ligand. And such that if you then take the two electrons away in your hypothetical dissociation, the ligand is left with a negative charge and the metal is left with a positive charge because we've technically now taken an electron away from the metal. So let's look at an example. We're going to go back to that cisplatin scenario again. Okay, so with cisplatin, we're going to focus now on the chlorine ligand because we know those are X-type ligands. You take away a chlorine in addition to its bonding electrons away from the metal center, and now we add a positive charge to that platinum. So the platinum has gained a positive charge and the chlorine leaves as a negatively charged species, an anionic species. And hence we call the chlorine an X-type ligand. So one of the unique properties of transition metals is that they tend to have varying oxidation states. And when it comes to organometallic complexes that occur in catalysis, these metals tend to change oxidation state as you go through the actual chemical reaction. To calculate the oxidation state of a metal within an organometallic complex, you take the charge of the complex, and then you add that charge of the complex to the charge that the metal would acquire if you hypothetically remove all the X-type ligands from that metal complex. So as an example, let's go back to our cisplatin case scenario again. So in this structure, the charge of the complex is 0. If it was a value that was not 0, you will be shown that it's either +1, a -1, +2, -3 charge complex. But in this case, it's 0. There are two X-type ligands on this complex, so the two chlorines, which means if you hypothetically take both of them off, the platinum will gain a +2 charge. As such, the oxidation state of the platinum in this particular complex is 2, a +2. And because the oxidation state of a metal tends to change, it is always important to be able to write and note the oxidation state along with the chemical symbol for that particular metal. So we would typically see things like PT2 or PT2 in Roman numerals to denote the oxidation state of the platinum within this particular complex. So another important property to be able to understand when you look at an organometallic complex is to understand how many unshared valence electrons, and so we want to know how many are not involved in any type of bonding. And this is usually reported as D superscript N, where N is that number of unshared electrons. You can readily calculate what that value is if you, one, know the number of valence electrons in the neutral atom. So if it was just like a regular atom, how many electrons would be in the outermost shell? And then if you subtract out the oxidation state of that metal, that will give you the number of unshared valence electrons in that particular metal. So once again, for example, if you have your cisplatin, we have to first figure out how many valence electrons are in platinum as a neutral atom. And this you can look at on your periodic table. Platinum is on group 10 of the periodic table. And so there are 10 valence electrons for neutral platinum. We've already determined that the oxidation state of platinum is 2, given that there are 2 X-type ligands on platinum, each contributing +1 to the platinum oxidation state. And so therefore, N is equal to 10 minus 2, which is equal to 8. And so from a reporting idea, we can say that cisplatin is a D8 complex. So it's giving an idea of how many electrons are available and unshared within that platinum complex. And then lastly, before we go into our first organometallic reaction, we can think about one more quantity that's actually really important for thinking about the stability of organometallic complexes, which is the electron counting. In other words, how many electrons are actually around that metal complex. So for main group compounds, so things like carbon, nitrogen, oxygen, and fluorine, we know that 8 electrons is sort of that nice stable electronic configuration for these atoms. So there's that octet rule for stability. For transition metals, because now you have 10 additional orbitals in the d orbital, we need 18 electrons to get to that noble gas configuration. And so therefore we have this 18 electron rule for stability. So if an organometallic complex has 18 electrons around that metal center, we would say that the organometallic complex is stable. So any deviation from that 18 electrons would suggest that that organometallic complex is less stable than it could be. So count the electrons. What you need to know is the value of N, which is the number of all unshared valence electrons around that metal, and add that value to 2 times the number of all the ligands that are actually coordinating or attached to the metal. And this value, highlighted in blue, represents all bonding electrons. So we have all unshared electrons and all bonding electrons. We add them up together, and that's our electron count. Okay, so let's look at an example. Okay, so consider this molecule, your palladium, that is coordinated to 4 triphenylphosphines. Keep in mind that phosphine or phosphorus, just like nitrogen, when you kick off the phosphine from the palladium complex, it's a neutral compound, and so phosphines are L-type ligands. So now we're going to find how many unshared valence electrons are on palladium in this complex. Recall that this value can be found by taking the number of valence electrons in a neutral palladium atom and subtracting it from the oxidation state of palladium in this complex. My hope is that if you look at the periodic table, you will see that palladium is in group 10, so there should be 10 electrons in the neutral palladium atom. And if you look at palladium in this complex, given that they are all L-type ligands and the entire complex has a charge of 0, the oxidation state of palladium in this complex is also 0, which means there are 10 electrons that are unpaired around this palladium valence shell. And so the electron count for this particular organometallic complex is 10 for the value of N plus 2 times 4, 4 representing the number of all the ligands in this particular complex, which gives us 18. And so we can say that the palladium with 4 triphenylphosphines coordinated to it is an 18 electron complex, which is telling us that this palladium is actually very stable from an electronic point of view because it has the full noble gas configuration around this particular metal. Okay, now let's do one more example. Let's compare the system we just looked at with the 4 triphenylphosphates around palladium. With this particular system, now we have a vinylic group bound to the palladium and a chlorine bound to the palladium, which means we now have 2 X-type ligands around that palladium. So convince yourself that if you take away the vinylic group, you would essentially put a negative charge on the carbon, highlighted here. And as well, if you take the chlorine out, you would put a negative charge on that chlorine. So these are X-type ligands. All right, so once again, the value of N, we need to find that, and then we sum that with not all the bonding electrons in this complex. So we're still dealing with palladium, so number of valence electrons in the neutral atom is still 10, but the oxidation state of this palladium is now 2, right? Because we have 2 X-type ligands that contributes 2 to the overall oxidation state of the palladium, which means that there are 8 unshared electrons around the palladium. It's a D8 complex. And so my electron count is 8 plus 2 times 4 for the number of all the ligands around the palladium, which gives us 16. And so we can say that this palladium-2 species is a 16 electron complex. It is therefore not as stable as it could be, which means that this could be a reactive intermediate, especially when we're thinking about a catalytic cycle. And we will see something like this as we go through organometallic reactions. All right, so now let's proceed with our first organometallic reaction, which is our Stille coupling. This particular reaction is incredibly powerful, and it's actually being used frequently and currently by practicing synthetic organic chemists. This is a reaction between an organotin or organostannane molecule. So this is a carbon-tin bond that we're talking about here. React that with an organohalide in the presence of a palladium catalyst would yield a coupling of those 2 R groups from the 2 reactants together, and then your side product, which is your halogenated tin complex. So note that Bu symbol that you're seeing on the organostannane is just butyl. That's an alkyl chain with 4 carbons. So it's just an alkyl chain. Please note that X is an organohalide or an equivalent of an organohalide, and so X can be a chloride, bromide, iodide, or a triflate, which is a sulfate group that has a CF3. That's a really good leaving group, and it can serve as essentially as a halogen replacement. The acronym or the short form for it is OTF for triflate. The traditional catalyst used for a Stille coupling is your palladium 0 catalyst that has 4 triphenylphosphine ligands. Please note that sometimes palladium 2 catalysts are used. So for example, here is this palladium that has 2 acetate groups, which is a carboxylate group bound to the palladium. However, it is well believed that the active catalyst is still a palladium 0, so these ligands sort of come off the palladium, and then some L-type ligands come back onto the palladium. Now over to our reagents. So you can prepare your organostannane or your organotin compound. If you start with an organohalide, you treat this with magnesium to form a Grignard reagent. Okay, this Grignard can now be treated with your organostannane with the chlorine leaving group, and now you can essentially do a displacement that would form your organostannane compound. Okay, so once again, organohalide, you form a Grignard. Notice how Grignard is a very reactive organometallic compound. We can then dress it down to an organostannane through a substitution. Stille couplings have a pretty wide substrate scope. Both your R and your R prime can be vinyl groups or aryl groups, and Your reagents are really selective in your Stille coupling. They will tolerate a wide variety of functional groups in the rest of the molecule. So carboxylic acids, amides, esters, nitriles, ethers, amines, alcohols, ketones, or aldehydes can all be present in your molecule, and your organotin compound will not react with any of those. It would exclusively react with your organohalide and then couple with that R group on the organohalide. Okay, so now let's dive a little bit deeper into the transformation of the Stille coupling, looking at the intermediate steps and what's going on to get you from the reactants to your products. The arrow pushing mechanism for these types of organometallic reactions are very dependent on the system, and so we're not going to actually push arrows here. All we're going to do is show the experimentally known and observed intermediates going through these catalytic cycles. But there are three major reaction mechanistic steps for your Stille coupling. The first is your oxidative addition. The second is called a transmetallation. And then the third is called a reductive elimination. And we're going to go through each of them one by one, and then we're going to put it together in a catalytic cycle. In the first step, your organohalide reacts with your active palladium complex. So note here that we've just used the word L, or the letter L, to represent a ligand attached to the palladium, because the identity of these ligands can actually change during the entire process. And so it is by convention that we pretty much only show the crucial reacting groups around the palladium complex. So for the purpose of this particular exercise, we're just going to use L2 to represent that there are at least two ligands on the palladium complex. So in this step, we see that the organohalide carbon-bromine bond has cleaved, and both the vinyl group and the bromine has now attached directly to the palladium center. As we can imagine, we have now introduced two X-type ligands to our palladium center, which means we have increased the oxidation state of the palladium by 2. And this is why we call this step an oxidative addition to the palladium center. In the transmetallation step, the oxidized palladium complex, the product of the oxidative addition step, now reacts with our organostannane. And I want you to look closely at the highlighted groups and what happens in this transformation. Okay, so notice what just happened. The phenyl group that was on our organostannane has now been transferred to the palladium. And so the group has gone from one metal to another metal. This has also moved the bromine that was on the palladium now to the tin. And so that's why we call it a transmetallation step, because groups are transferring from one metal to another metal. It's important to note that this is the rate determining step of this reaction. As you can imagine, the idea of transferring R groups from one metal to another metal is likely to be a relatively slow step. And from experimental observations, vinyl groups transfer the fastest, followed by aryl groups, followed by allyl group, and then way down there in rates are alkyl groups. Alkyl groups actually almost rarely transfer. And so we can rest assured, that's why we really don't use alkyl groups in this particular reaction, because they don't tend to transfer in the transmetallation step. And then lastly, in your reductive elimination step, during this process, both of the R groups that have now been attached to the exact same palladium now form a new sigma bond between the two partners, which is your final product of your coupling reaction. And then importantly, your palladium catalyst returns back to the catalytic cycle for another cycle of this reaction. So given what we've just seen, we can indeed turn this into a catalytic cycle. In the initial step, we said it's an oxidative addition where the organohalide comes in and adds on to your palladium complex. And here's how we can represent this elementary step in our catalytic cycle. So note the arrows flowing in, you're flowing in with the organohalide, and then we're ending up at our oxidative addition intermediate. At this point, you now have your transmetallation with your organostannane, so we can represent this step as such on a catalytic cycle. And here is it. Here's how we can represent this flow. So notice that as we bring in the organostannane, we kick out the brominated organostannane, okay? And then we form our transmetallic product. And then at this stage, we have our reductive elimination, and we can show this way on a catalytic cycle. And we can show the reductive elimination as such on a catalytic cycle. And that is our major product of the reaction that gets kicked off the catalytic cycle. And then we see the cycle. So the palladium can then come back again and do another round of oxidative addition, transmetallation, and reductive elimination. And so that's what we have here. And so the last thing we would note about Stille couplings, that just like our previous organometallic reactions we've learned, Stille couplings are also stereospecific, which means that the stereoconfiguration of our reactants dictates the stereoconfiguration of our products. And so, for example, if you have this particular configuration of your organostannane, and you react that with this particular configuration of your organohalide, keeping in mind that the two starred carbons are the ones that are going to end up forming your CC bond formation in your coupling reaction. Using your palladium 0 catalyst, your Stille coupling will occur and will form this particular product where we've retained the stereoconfiguration of our two reactants within the product. So this is similar to our coupling reactions with organocuprates or lithium dialkyl-cuprates. You get a retention of stereoconfiguration in your coupling with your stannane as well. Okay, so we've gone through an introduction to organometallic complexes. We've identified what a transition metal is, how to do some electron counting around transition metals. We know the different kinds of ligands that we can have on a transition metal, an X versus an L type ligand. We've gone through the Stille coupling synthesis. We've identified the elementary steps in the mechanism, our oxidative addition, our transmetallation, our reductive elimination, and we've addressed the stereospecificity of the Stille coupling reaction. Okay, thank you so much for watching this video, and I will see you in class.